Hi folks, so today we're going to be introducing chapter 7, which is looking at exponential and logarithmic functions, but today we're going to look at just exponential. So this form right here is the form of an exponential function. So to the right here, it's going to lay out what each of those letters mean. So A is the coefficient, and a reminder, coefficient just means the numerical value that would sit in front of something else. Okay, B is going to be the base that's eventually going to be raised to an exponent, and X is going to be the exponent. So in the last chapter, we talked a lot about polynomial functions, and they would have the variable X, but as the base. So often it would be like X with an exponent. This time, in exponential functions, the X becomes the exponent. Okay, so this is going to look slightly different when we have the X variable in the spot of an exponent. And what that ends up creating is what's called a horizontal asymptote. So horizontal just means a line that goes left and right. And an asymptote is a line or a value that can be approached but never reached. So to the right here is just an example of an exponential function. So the blue line, you see it's steadily increasing exponentially. So it's becoming larger and larger and larger and larger. And if you were to continue this graph to the left, this blue line would actually never touch the x-axis because there is an invisible asymptote. Okay, I tried to draw it as a dashed red line here at y is equal to 0, meaning the line's going to get really close to y is equal to 0, but it's never actually going to reach it. Okay, so now we're just going to look at the graphs of a couple exponential functions to see if we can find some trends. So I am using Desmos. I'm just going to turn them on and off and we'll fill in this table. So for this first one, I have y is equal 4, 2 to the x. So a little sketch that would just be draw what this looks like. And I'm going to say it looks like it's crossing at the point 0, 4. Okay, so it's saying, is there any x-intercepts? Well, a reminder, on these graphs, it's never going to show you the asymptote. Okay, but most of the ones we're going to study are going to have an asymptote at y is equal to 0, unless you see something added or subtracted from the exponential function. So if there is an asymptote there, that means there is no x-intercept, none whatsoever. It never touches. The y-intercept is at 0, 4. It goes from Q2 to Q1. The trend, I'm just asking, is it increasing or decreasing? So this one, it starts on the left low and it's going up. So I'm going to use the word increasing. Okay, the domain, it goes all the way left, all the way right. So negative infinity to infinity. And the range, so it starts at 0 and it goes up. But it doesn't actually touch 0. So when I'm writing this, you're either going to write from 0 to infinity, or you have to write that y is greater than 0. Both those would work. Okay, I'm going to skip the second one, but I'll show you a super quick sketch of what it would be without filling in the rest. What you would need to know is that here, if I zoom in, the y-intercept is at 7. Oh, sorry. And the horizontal asymptote would still be 0. This would be the same. This would be the same. All these would be the same as the previous. And it would look something like this. So it would just cross at 0, 7. Okay. The graph almost looks the same. It just kind of increases a little more quickly. No x-intercepts. So now let's go to what happens when the base becomes a fraction. So let's turn that one on. So you might notice that the graph, instead of looking like it's increasing, now looks like it's decreasing. So again, it's never going to be able to hit y is equal to 0, so there cannot be any x-intercepts. Okay, and I'll check here, the y-intercept is at 0, 3. It is still going from Q2 to Q1, okay? But this time we'll say it's decreasing because it starts at a large value and slowly decreases over time. And the domain and the range stay the same. So you can assume, without even really filling in much for the next one, that a lot of it's going to look the same because we have another fraction. And this time we have a y-intercept of 5. Okay, still an asymptote at 0. It's still Q2 to Q1. It's decreasing. And the domain and the range remain the same. So the general conclusions of what we just discovered, specifically about what A and the base are. Okay, so if we have a graph where the B value is greater than 1, it's going to look something like this, like it's increasing. But if we have a fraction, so I'm going to rate that as something between 0 and 1, it's going to look like it's decreasing. In neither scenario did we have x-intercepts. Okay, in both scenarios, the y-intercept was 0. The horizontal asymptote was 0. Okay, in both scenarios, the y value was always this, which we are calling A. So I'm just going to rate it as 0A. Okay. It always goes Q2 to Q1. We'll talk about when it might not in a moment. Okay, in the first scenario, when the B value is greater than 1, it's increasing. When it's between 0 and 1, it's decreasing. And these remain the same. Okay, so those are kind of the general conclusions that we should come to. So what we do need to remember is that when the base value is greater than 1, we should see an increasing graph. What we're going to start to call this is going to be called the growth curve. So we'll start using growth instead of increasing. If it's between 0 and 1, so those fractions or decimals, we're going to say it's decreasing. And when it comes to exponential, we usually use the word decay curve. And if it's equal to 1, we didn't do one like this, but if we think of some number with a 1 to a power of x, well, any value 1 to any exponent in the universe is just going to be 1. So this actually just creates a straight line. So usually if we're studying exponentials, a straight line wouldn't be considered exponential, so we don't normally see a base of 1. Okay, so you're more likely to see this first case or this third case. Okay, so a growth curve, we said that's when B is greater than 1. A growth curve can look like two things. The ones we were seeing before were looking like this. So it kind of is slowly growing over time. As the x values increase, the y values also increase. Another way that you can represent a growth curve that is exponential, and we'll talk about where that comes from, is like this. Again, it's growing steadily over time. It's just on the opposite side of the axis. That's it. Again, with the decay curve, the ones we were seeing before looked like this. Okay, the values are slowly decreasing over time. So as the x values increase, the y values should be decreasing. Okay, but it can also look like this if you're on the opposite side of the y-axis. Because again, these y values are decreasing. Okay, so when would we get those blue curves? That's the next thing we're going to look at. So I'm going to graph this function. So I'm first of all graphing it as if it was positive. So if this was positive, it would look like this. It would look like a growth curve. Okay, and it would look like growth on the top. When I introduce a negative in front of it, notice that it flips, or we call that reflecting, across the y-axis. So what was once up here is now down here. So originally when it was positive, it looks like this, and it looks like it would be a growth curve. Okay, but because it's been reflected, and now it's down here, this is slowly decreasing over time. This is decaying. So I'm going to say this is a decay curve. So one thing I like to remember is I always look at the base first and I say this is growth. But if I see there's a reflection, then I know it's going to be the opposite of what I think. So it'll become a decay curve. That's only when you see the negative. So in this case, the domain stays the same. We're still going to go negative infinity to infinity. But this time the range starts at really small y values and ends at 0. So I'm going to write either negative infinity to 0, or you can say that the y values are less than 0. Both those mean the same thing. We can do the same thing for this one. So I'm first of all going to graph it as if it's positive. So if it was positive, it would look like a decay curve, but it's negative. So let me put a negative in front. And we see it flips and is actually going to look like this. Okay, and which becomes a growth curve. So once again, what I would do is I'd look at the base. I see this to me would be decay because it's between 0 and 1. But because it's reflected, it's the opposite of what I think. So it's growth. So the domain and the range would be the same when they're reflected. So the overall summary, there's not going to be x-intercepts unless we move this up and down, which I'm not planning to. The x-intercept is always the a value. Okay, the end behavior, if there's only a positive a value, it goes Q2 to Q1. If there's a negative a value, it goes Q3 to Q4. Okay, so that's what this is saying. If it's reflection, if it's reflected, it's at the bottom two quadrants. Okay, it's a growth curve when the b value is greater than 1, but it's a decay curve when the b value is between 0 and 1. So some decimal or fraction between 0 and 1. So we're going to do just a couple practice ones to make sure we understand. So this one is asking me if it's growth or decay. So I always look at the b value. So this is between 0 and 1, so decay. And because there's no negative in front, I can confidently say it is decay. And then the y value is always the first value we see. So it'd be 0, 2 would be the y-intercept. Okay, now, second one. First off, this would normally be growth because it's greater than 1, but there's a negative. So it's the opposite of what I think. So it must be decay. And the y-intercept is the value that's sitting in front of the brackets. So it would be 0 minus 5. Okay. For this one, I would say growth because it's greater than 1. Okay. And there's no negative, so it must be growth. And the y-intercept is this value sitting in front of the bracket, so 0, 0.3. And last but not least, this would normally be decay, but because there's a negative, it's the opposite, so growth, and the y-intercept is -2. Now, it wants us to create a function, an exponential function for this equation. So I'm going to rewrite. Okay, remember A is just our y-intercept. So if we can figure out which point here is our y-intercept, we're set for at least the a value. And a y-intercept is always 0 followed by a number. So an x and a y. So that must be this, 0, 20. So our a value is 20. And the way we get our b value, and we're going to practice this in detail on Monday, is by looking at the y values and seeing what you have to multiply by each time. So between 5 and 10, I have to double, and then double and double, and that pattern continues, which makes my b value 2. Okay, we're going to create strategies to do that in the following classes. Okay, last one's here. So without graphing, can we state the properties? So what I mean by this is I would say, okay, this is decay and it's not reflected. So I'd create a little sketch for myself. It's not reflected, so it must be in the top 2 quadrants and it's decaying. So it looks something like that. So the domain is -infinity to infinity. And the range is we start at a y value of 0 and we go to infinity. Now the end behavior, it's in those top 2 quadrants, so Q2 to Q1. And is it growth or decay? Well, this one's definitely decaying, so it's decreasing over time. The y-intercept is the first value in front of the bracket, so 0, 3. And the x-intercept, there is none, trying to trick us. Okay. And then for the second one, this would be a decay curve. So before anything else, it would look something like this, but it's reflected. So I'm going to take this graph and I'm going to flip it across the x-axis. Sorry, yeah, across the x-axis. So it's going to look like this. Okay. So the domain stays the same, but this time the range goes from -infinity to 0. Okay. The end behavior is in the bottom 2 quadrants, so Q3 to Q4. Because it's growing, I'm going to call this a growth curve or a increasing curve. The y-intercept, the value in front of the brackets, and no x-intercept. So you can see even without graphing, you can follow the trends that we see every time. And then last one, again, without graphing, can we try to match the graphs below? So automatically, when I look at these, I'd look at the y-intercepts, where it crosses, and if it's growth or decay. So for this one, it has a y-intercept of 0, 3, and this should be decay. Okay, for this one, y-intercept of 0, 4, and the 3 means it's a growth. I'll just do this for all of them. So this would be 0, 4. And because I have a decimal that's less than 1, this would be decay. This would be 0, 2. And the 4 would mean growth. So first of all, let's start with D, because I just have it here. The y-intercept is at 4. So we are between this option and this option. Okay, but in the last graph of D, it is decaying, so slowly decreasing. So that means the only one that has a y-intercept of 4 and is decreasing is the third option. So I'm going to remove that as an option. Then for this one, it has a y-intercept of 3. And there's only one of these that has a y-intercept of 3. It's this one. So even without doing anything else, I automatically can associate 1, and we can validate, yeah, it's definitely decaying. So we can be happy with our choice. Okay. Next up, this one has a y-intercept of 4, and it's growing. So it must be this second one, which leaves us with a y-intercept of 2 and growing. Y-intercept of 2, that's good, and it's growth. So that must be the fourth. Okay. So with this in mind, this is the basics of exponential functions. You'll be doing some practice today and Monday, and then we'll get back together and talk about how we can create equations using this. Okay, good luck and be very productive.